In particle physics, antimatter is material composed of antiparticles, which have the same mass as particles of ordinary matter but have opposite charge and other particle properties such as lepton and baryon number. Encounters between particles and antiparticles lead to the annihilation of both, giving rise to varying proportions of high-energy photons, neutrinos, and lower-mass particular antiparticle pairs. Setting aside the mass of any product neutrinos, which represent released energy which generally continues to be unavailable, the end result of annihilation is a release of energy available to do work, proportional to the total matter and antimatter mass, in accord with the mass-energy equivalence equation, E equals mc2. Antiparticles bind with each other to form antimatter just as ordinary particles bind to form normal matter. For example, a positron and an antiproton can form an antihydrogen atom. Physical principles indicate that complex antimatter atomic nuclei are possible, as well as antiatoms corresponding to the known chemical elements. To date, however, antiatoms more complex than antihelium have neither been artificially produced nor observed in nature. Studies of cosmic rays have identified both positrons and antiprotons, presumably produced by high-energy collisions between particles of ordinary matter. There is considerable speculation as to why the observable universe is apparently composed almost entirely of ordinary matter, as opposed to a more symmetric combination of matter and antimatter. This asymmetry of matter and antimatter in the visible universe is one of the greatest unsolved problems in physics. The process by which this asymmetry between particles and antiparticles developed is called baryogenesis. Antimatter in the form of antiatoms is one of the most difficult materials to produce. Antimatter in the form of individual antiparticles, however, is commonly produced by particle accelerators and in some types of radioactive decay. History of the concept. The idea of negative matter appears in past theories of matter that have now been abandoned. Using the once popular vortex theory of gravity, the possibility of matter with negative gravity was discussed by William Hicks in the 1880s. Between the 1880s and the 1890s, Carl Pearson proposed the existence of squirts and sinks of the flow of ether. The squirts represented normal matter and the sinks represented negative matter. Pearson's theory required a fourth dimension for the ether to flow from and into. The term antimatter was first used by Arthur Schuster in two rather whimsical letters to Nature in 1898, in which he coined the term. He hypothesized antiatoms, as well as whole antimatter solar systems, and discussed the possibility of matter and antimatter annihilating each other. Schuster's ideas were not a serious theoretical proposal, merely speculation, and like the previous ideas, differed from the modern concept of antimatter in that it possessed negative gravity. The modern theory of antimatter began in 1928, with a paper by Paul Dirac. Dirac realized that his relativistic version of the Schrödinger wave equation for electrons predicted the possibility of anti-electrons. These were discovered by Carl D. Anderson in 1932 and named positrons. Although Dirac did not himself use the term antimatter, its use follows on naturally enough from anti-electrons, antiprotons, etc. A complete periodic table of antimatter was envisaged by Charles Janet in 1929. Notation: one way to denote an antiparticle is by adding a bar over the particle's symbol. For example, the proton and antiproton are denoted as P and P, respectively. The same rule applies if one were to address a particle by its constituent components. A proton is made up of odd quarks, so an antiproton must therefore be formed from odd antiquarks. Another convention is to distinguish particles by their electric charge. Thus, the electron and positron are denoted simply as A and E+, respectively. However, to prevent confusion, the two conventions are never mixed. Origin and asymmetry. Almost all matter observable from the Earth seems to be made of matter rather than antimatter. If antimatter-dominated regions of space existed, the gamma rays produced and annihilation reactions along the boundary between matter and antimatter regions would be detectable. Antiparticles are created everywhere in the universe where high-energy particle collisions take place. High-energy cosmic rays impacting Earth's atmosphere produce minute quantities of antiparticles in the resulting particle jets, which are immediately annihilated by contact with nearby matter. They may similarly be produced in regions like the center of the Milky Way and other galaxies, where very energetic celestial events occur. The presence of the resulting antimatter is detectable by the 2 gamma rays produced every time positrons annihilate with nearby matter. The frequency and wavelength of the gamma rays indicate that each carries 511 keV of energy. Recent observations by the European Space Agency's integral satellite may explain the origin of a giant cloud of antimatter surrounding the galactic center. The observations show that the cloud is asymmetrical and matches the pattern of X-ray binaries, mostly on one side of the galactic center. While the mechanism is not fully understood, it is likely to involve the production of electron-positron pairs, as ordinary matter gains tremendous energy while falling into a stellar remnant. Antimatter may exist in relatively large amounts in faraway galaxies due to cosmic inflation in the primordial time of the universe. Antimatter galaxies, if they exist, are expected to have the same chemistry and absorption and emission spectra as normal matter galaxies, and their astronomical objects would be observationally identical, making them difficult to distinguish. NASA is trying to determine if such galaxies exist by looking for X-ray and gamma-ray signatures of annihilation events in colliding superclusters. Natural production: positrons are produced naturally in I² plus decays of naturally occurring radioactive isotopes and in interactions of gamma quanta with matter. Neutrinos are another kind of antiparticle created by natural radioactivity. Many different kinds of antiparticles are also produced by cosmic rays. Recent research by the American Astronomical Society has discovered antimatter originating above thunderstorm clouds. Positrons are produced in gamma-ray flashes created by electrons accelerated by strong electric fields in the clouds. Antiprotons have also been found to exist in the Van Allen belts around the Earth by the Pamela module. Antiparticles are also produced in any environment with a sufficiently high temperature. During the period of baryogenesis, when the universe was extremely hot and dense, matter and antimatter were continually produced and annihilated. The presence of remaining matter, and absence of detectable remaining antimatter, also called baryon asymmetry, is attributed to CP violation, a violation of the CP symmetry relating matter to antimatter. The exact mechanism of this violation during baryogenesis remains a mystery. Positrons can be produced by radioactive I² plus decay, but this mechanism can occur both naturally and artificially. Observation in cosmic rays: satellite experiments have found evidence of positrons and a few antiprotons in primary cosmic rays, amounting to less than 1% of the particles in primary cosmic rays. These do not appear to be the products of large amounts of antimatter from the Big Bang, or indeed complex antimatter in the universe. Rather, they appear to consist of only these 2 elementary particles, newly made in energetic processes. Preliminary results from the presently operating alpha magnetic spectrometer on board the International Space Station show that positrons in the cosmic rays arrive with no directionality, and with energies that range from 10 GeV to 250 GeV, with the fraction of positrons to electrons increasing at higher energies. These results on interpretation have been suggested to be due to positron production in annihilation events of massive dark matter particles. Antiprotons arrive at Earth with a characteristic energy maximum of 2 GeV, indicating their production in a fundamentally different process from cosmic ray protons, which on average have only 1/6 of the energy. There is no evidence of complex antimatter atomic nuclei, such as antihelium nuclei, in cosmic rays. These are actively being searched for. A prototype of the AMS-02 designated AMS-01, was flown into space aboard the Space Shuttle Ear Discovery on STS-91 in June 1998. By not detecting any antihelium at all, the AMS-01 established an upper limit of 1.1 10^6 for the antihelium to helium flux ratio. Artificial production: positrons. Positrons were reported in November 2008 to have been generated by Lawrence Livermore National Laboratory in larger numbers than by any previous synthetic process. A laser drove electrons through a millimeter radius gold target's nuclei, which caused the incoming electrons to emit energy quanta that decayed into both matter and antimatter. Positrons were detected at a higher rate and in greater density than ever previously detected in a laboratory. Previous experiments made smaller quantities of positrons using lasers and paper-thin targets. However, new simulations showed that short, ultra-intense lasers and millimeter-thick gold are a far more effective source. Antiprotons, antineutrons, and antinuclei. The existence of the antiproton was experimentally confirmed in 1955 by University of California, Berkeley physicists Emilio Segre and Owen Chamberlain, for which they were awarded the 1959 Nobel Prize in Physics. An antiproton consists of two up antiquarks and one down antiquark. The properties of the antiproton that have been measured all match the corresponding properties of the proton, with the exception of the antiproton having opposite electric charge and magnetic moment from the proton. Shortly afterwards, in 1956, the antineutron was discovered in proton-proton collisions at the Bevatron by Bruce Cork and colleagues. In addition to antibaryons, antinuclei consisting of multiple bound antiprotons and antineutrons have been created. These are typically produced at energies far too high to form antimatter atoms. In 1965, a group of researchers led by Antonino Saikichi reported production of nuclei of antideuterium at the proton synchrotron at CERN. At roughly the same time, observations of antideuterium nuclei were reported by a group of American physicists at the alternating gradient synchrotron at Brookhaven National Laboratory. Antihydrogen atoms. In 1995, CERN announced that it had successfully brought into existence 9 antihydrogen atoms by implementing the SLAC Fermilab concept during the PS210 experiment. The experiment was performed using the low-energy antiproton ring, and was led by Walter Ouellette and Mario Macri. Fermilab soon confirmed the CERN findings by producing approximately 100 antihydrogen atoms at their facilities. The antihydrogen atoms created during PS210 and subsequent experiments were extremely energetic and were not well suited to study. To resolve this hurdle, and to gain a better understanding of antihydrogen, two collaborations were formed in the late 1990s, namely, Athena and ATRAP. In 2005, Athena disbanded and some of the former members formed the Alpha collaboration, which is also based at CERN. The primary goal of these collaborations is the creation of less energetic antihydrogen, better suited to study. In 1999, CERN activated the antiproton decelerator, a device capable of decelerating antiprotons from 3.5 GeV to 5.3 MeV. Still too hot to produce study-effective antihydrogen, but a huge leap forward. In late 2002 the Athena project announced that they had created the world's first cold antihydrogen. The ATRAP project released similar results very shortly thereafter. The antiprotons used in these experiments were cooled by decelerating them with the antiproton decelerator, passing them through a thin sheet of foil, and finally capturing them in a Penning-Moorburg trap. The overall cooling process is workable, but highly inefficient. Approximately 25 million antiprotons leave the antiproton decelerator and roughly 25,000 make it to the Penning-Moorburg trap, which is about 1 or 1,000 or 0.1% of the original amount. The antiprotons are still hot when initially trapped. To cool them further, they are mixed into an electron plasma. The electrons in this plasma cool via cyclotron radiation, and then sympathetically cool the antiprotons via Coulomb collisions. Eventually, the electrons are removed by the application of short-duration electric fields, leaving the antiprotons with energies less than 100 MeV. While the antiprotons are being cooled in the first trap, a small cloud of positrons is captured from radioactive sodium in the Serco-style positron accumulator. This cloud is then recaptured in a second trap near the antiprotons. Manipulations of the trap electrodes then tip the antiprotons into the positron plasma, where some combine with antiprotons to form antihydrogen. This neutral antihydrogen is unaffected by the electric and magnetic fields used to trap the charged positrons and antiprotons, and within a few microseconds the antihydrogen hits the trap walls, where it annihilates. Some hundreds of millions of antihydrogen atoms have been made in this fashion. Most of the sought-after high-precision tests of the properties of antihydrogen could only be performed if the antihydrogen were trapped, that is, held in place for a relatively long time. While antihydrogen atoms are electrically neutral, the spins of their component particles produce a magnetic moment. These magnetic moments can interact with an inhomogeneous magnetic field. Some of the antihydrogen atoms can be attracted to a magnetic minimum. Such a minimum can be created by a combination of mirror and multipole fields. Antihydrogen can be trapped in such a magnetic minimum trap. In November 2010, the Alpha collaboration announced that they had so trapped 38 antihydrogen atoms for about a sixth of a second. This was the first time that neutral antimatter had been trapped. On April 26, 2011, Alpha announced that they had trapped 309 antihydrogen atoms, some for as long as 1,000 seconds. This was longer than neutral antimatter had ever been trapped before. Alpha has used these trapped atoms to initiate research into the spectral properties of the antihydrogen. The biggest limiting factor in the large-scale production of antimatter is the availability of antiprotons. Recent data released by CERN states that, when fully operational, their facilities are capable of producing 10 million antiprotons per minute. Assuming a 100% conversion of antiprotons to antihydrogen, it would take 100 billion years to produce 1 gram or 1 mole of antihydrogen. Antihelium, Antihelium-3 nuclei were first observed in the 1970s in proton-nucleus collision experiments and later created in nucleus-nucleus collision experiments. Nucleus-nucleus collisions produce antinuclei through the coalescence of antiprotons and antineutrons created in these reactions. In 2011, the STAR detector reported the observation of Antihelium-4 nuclei. Preservation: antimatter cannot be stored in a container made of ordinary matter because antimatter reacts with any matter it touches, annihilating itself and an equal amount of the container. Antimatter in the form of charged particles can be contained by a combination of electric and magnetic fields, in a device called a pinning trap. This device cannot, however, contain antimatter that consists of uncharged particles, for which atomic traps are used. In particular, such a trap may use the dipole moment of the trapped particles. At high vacuum, the matter or antimatter particles can be trapped and cooled with slightly off-resonant laser radiation using a magneto-optical trap or magnetic trap. Small particles can also be suspended with optical tweezers, using a highly focused laser beam. In 2011, CERN scientists were able to preserve antihydrogen for approximately 17 minutes. Cost: scientists claim that antimatter is the costliest material to make. In 2006, Gerald Smith estimated $250 million could produce 10 milligrams of positrons. In 1999, NASA gave a figure of $62.5 trillion per gram of antihydrogen. This is because production is difficult, and because there is high demand for other uses of particle accelerators. According to CERN, it has cost a few hundred million Swiss francs to produce about 1/1000th of a gram. Several studies funded by the NASA Institute for Advanced Concepts are exploring whether it might be possible to use magnetic scoops to collect the antimatter that occurs naturally in the Van Allen belt of the Earth, and ultimately, the belts of gas giants, like Jupiter, hopefully at a lower cost per gram. Uses: medical, matter-antimatter reactions have practical applications in medical imaging, such as positron emission tomography. In positive beta decay, a nuclide loses surplus positive charge by emitting a positron. Nuclides with surplus positive charge are easily made in a cyclotron and are widely generated for medical use. Antiprotons have also been shown within laboratory experiments to have the potential to treat certain cancers, in a similar method currently used for ion therapy. Fuel: isolated and stored antimatter could be used as a fuel for interplanetary or interstellar travel as part of an antimatter-catalyzed nuclear pulse propulsion or other antimatter rocketry, such as the Redshift rocket. Since the energy density of antimatter is higher than that of conventional fuels, an antimatter-fueled spacecraft would have a higher thrust-to-weight ratio than a conventional spacecraft. If matter-antimatter collisions resulted only in photon emission, the entire rest mass of the particles would be converted to kinetic energy. The energy per unit mass is about 10 orders of magnitude greater than chemical energies, and about 3 orders of magnitude greater than the nuclear potential energy that can be liberated, today, using nuclear fission, and about 2 orders of magnitude greater than the best possible results expected from fusion. The reaction of 1 kg of antimatter with 1 kg of matter would produce 1.8 A, 1017 a J of energy, or the rough equivalent of 43 megatons of TNT, slightly less than the yield of the 27,000 a kg Tsar bomb, the largest thermonuclear weapon ever detonated. Not all of that energy can be utilized by any realistic propulsion technology because of the nature of the annihilation products. While electron-positron reactions result in gamma-ray photons, these are difficult to direct and use for thrust. In reactions between protons and antiprotons, their energy is converted largely into relativistic neutral uncharged pions. The neutral pions decay almost immediately into high-energy photons, but the charged pions decay more slowly and can be deflected magnetically to produce thrust. Note that charged pions ultimately decay into a combination of neutrinos and unstable charged muons, with the muons then decaying into a combination of electrons, positrons and neutrinos. 0.78 equals 0.74. Weapons. Antimatter has been considered as a trigger mechanism for nuclear weapons. A major obstacle is the difficulty of producing antimatter in large enough quantities, and there is no evidence that it will ever be feasible. However, the U.S. Air Force funded studies of the physics of antimatter in the Cold War, and began considering its possible use in weapons, not just as a trigger, but as the explosive itself. See also, antimatter comet, ambiplasma, particle accelerator, antiparticle, antihydrogen, gravitational interaction of antimatter. References. Further reading, G. Fraser. Antimatter, The Ultimate Mirror. Cambridge University Press. ISBN A978-0-521-65252-0. Antimatter production for near-term propulsion applications. External links. Antimatter on In Our Time at the BBC. Freeview video. Antimatter by the Vega Science Trust and the BBC OU. CERN Weekcasts, What is Antimatter? FAQ from CERN with lots of information about antimatter aimed at the general reader, posted in response to antimatter's fictional portrayal in Angels and Demons. What is direct CP violation? Animated illustration of antihydrogen production at CERN from the Exploratorium.